I want to start just by introducing you to how you look at the arrays or the matrices before we get into all the matrix multiplication and everything. So the first thing we'll just look at is a neuron within some time frames. And a great way to think about it is like a raster. So we can have a raster of some, let's think about it as there's a neuron here and it's getting input from some input neuron, and it's some weight, and then it's gonna give some output. So let's call that N out, and then the neural input is here, and that's just what we're gonna simulate. And what we're gonna be assessing is we're gonna be thinking of it as time bins, like kind of what you were doing in your honors. So think of this as some time frame with n number of bins, and let's say in one bin we're gonna get this input, and then we're gonna be monitoring what's the output. So let's put that in green, and the output is maybe here. So let's just simulate this for an example. So we have some n number of bins. Let's just say we have 150 bins, and we want to initialize the time frame. So a time frame is equal to zeros, one row, and an n number of bins of columns. So I want to keep your eye on the whole thing, so I'm going to make a figure, and I'm going to plot, and instead of plot, let's have a heat map. Okay, heat map of the time. Now it's all zeros and just one row. So let's create our input sequence. We can have it so that the n in is equal to the time frame, and then n in, let's go like this, n in at maybe 10 is equal to 1. So at point 10 we get a 1, and then we can say put that as the heat map. I can run this. Now I can say just at that time point I want to see it color map as hot, just so it looks better. Okay, here we go. So it's all black, and then at point 10 we get a 1 as an input. But then how do we get the output? Well, we initialize the n output as just the time frame again, but then we're going to loop through all the sequences and check what the input was at the previous step. So for I equals 2, we're going to go for the number of bins, and for n out at time I, we're going to say that's equal to some weight times the input at the previous time step, so I minus 1. So now we're just going to get, and it's going to be a pretty boring plot that we get right now, because we're just shifting everything by 1. We didn't initialize a weight, so let's just have the weight equals 0.8 or something. Doesn't matter. And now I can see, oops. And now I can see that we just moved it by 1. And now instead of being 1, it's a 0.8. Let's just label these. Okay. Now let's make something interesting happen. So let's make, instead of just one spike, let's have random spikes, like a random number of spikes. So instead of n in equals 10 and 10 equals 1, so let's say there are some n inputs. Let's just say there are 20 inputs, and n in at input indexes. We have to say where the index is. So let's have a random number. I'll just show you how random works. So if I say rand2, it's going to make a 2 by 2 of random numbers between 0 and 1. So if I say rand1 point, so an n inputs would be 20. So let's say rand1 point n inputs. We're going to get 20 numbers that are between 0 and 1. So I just have to multiply them by the number of bins and then seal that so that it doesn't go from 0, because we can't have a 0 index. So here we go. Now we have some input indexes, and they are between 1 and 150, I guess. And now those indexes are going to be equal to this input. And now if we run it, we can see that oops. Here we go. We can see that we're getting the same thing, but now there's just a shift. Let's have 10. So why am I doing this? Because the Aplysia gill reflex. So Aplysia gill withdrawal. Alyssa, what? Here we go. So there is an animal that if you touch its siphon, it's going to withdraw its gill. First time you touch the gill, its reflex, let's say this is 0 and this is max reflex, it's going to start here, and then if you touch again, it's going to go down, 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 and then if you leave it for some time, then it's going to recuperate. This is called habituation. So let's say there is some factor, let's say time factor, and that is normally 1. So normally everything just gets multiplied by 1. So let's say this time factor times this happens. But if the previous n out was greater than 0, then the time factor is going to become the time factor minus some decay times the time factor. So it's going to decay away a bit. And let's set this decay as 0.4 just to begin with, and we'll see what happens. Now, if we play this out, you'll see that it's just going to decay and then never return again, because the time factor is always changing. So let's just see that. So here you see it's just decaying, and it has no regard for how close it is. It's just if there was a spike, it's going to decay, and if there's another spike, it's going to decay. But the first spike that we see is 0.8. So what we want is we want this time factor to return to its original value, So every time step, we're gonna check. So time factor is gonna become the time factor, and then it's gonna return back. So let's say it's gonna return by some return factor. And that's slower, let's call that 0.1 or something, times the time factor. Now there's something interesting that might happen here. What might actually happen is we get over 1, which is not something that would happen, right? And it's happening every single step. So we check if time factor is over 1, then the time factor is just going to be equal to 1. And we say end. So we don't want it to go over 1. But it can decay. So let's decrease this again and run this. And here we see. So, and let's increase our inputs a bit so we can see this maybe more interestingly. Let's increase the return factor again and maybe get some interesting behavior happening. So it's not obvious what's happening, but if we dial this down just a bit, we can see that if there are spikes happening really close, it's going to get depressed a lot. But if there's a large space between them, they're not going to get depressed as much. So having some time to recuperate will allow this withdrawal reflex to recuperate. But if you stimulate again and again and again and again within a short period, it's going to decay even more. And if we make the decay higher and the recuperation even lower, and maybe increase the time frame, so let's say, I don't know, 250, increase the inputs to 35, and just look what that looks like. So now it's just like dying. Not as exciting. Let's call it 235 again. And that's interesting. So the decay factor is too high for it to look interesting. Go again. This is a bit better. Increase the return factor again to 1. Now it looks more interesting. But to understand what's really going on, we can make a time factor check and make that equal to the time frame. And because time factor at 0.0 is 1, we're going to say at 0.1 is equal to 1, and then just log the time factor. So we can actually assess it. So now we're going to have 3 subplots. And the final subplot is going to be the time factor check. And now I can see what's actually happening. So when it's 1, it's returned to baseline. So we can increase the return factor even more, and we can see it's more white because it's faster returning. We can increase the decay even more, like 7, and we can see it decays too fast. And then we can have it not a function of how large the time factor is, and we can just have it as a pure return factor. So now it's going to increase by 0.1 for every tick, except if there is a spike within the bin. So can make it 0.5 and see how that happens. So there's a lot you can play with, and a lot of ways you can affect the output neuron just by adding these few little adjustments of a weight being added, or some time factor dependency on the input or the output cell firing. So what you can actually think of us having finished here is we have two neurons, and this neuron is gonna stimulate this one by some weight times its input, and it's going to give an output at a different time. So this happens at T1, this happens at T2, but at T3 is a function of if this happened, right? So it's not just the simple shift by one that we did previously. Now it's actually computing and integrating. So with this in mind, we'll move on to more complex stuff, but it's really not super complex. We just need a little bit of matrix multiplication knowledge before we move on. So that's going to be the next step. And before we get into that, I'll show you what we actually can do with it.